everyone. Thank you so much for coming, and thank you so much to Upperbound for having me today. My name is Kateryna Nekhomiazh. I'm a solutions architect at NVIDIA, and I'm very excited to talk to you about our platform and what NVIDIA does for deep learning acceleration. So throughout the last decade, artificial intelligence made a huge jump from just being a research curiosity to transforming almost every industry, or I think we can say every industry. So it made a huge leap, and it does not stop to advance actively. And we really need to keep up with it as our models become larger and larger and AI's demands grow. So in my talk today, I want to tell you about NVIDIA's platform, what great tools we have that you can use to accelerate your workflows, to do what you do faster, and also to culminate and lead it to where is the next frontier for AI, which we believe is physical AI. I will tell you about Cosmos World Foundation models that our research teams are actively developing. So I'd like to begin with that NVIDIA is not just a chip company. We started as a chip company and developed GPUs for video graphics. But throughout the years, we understood that to power hardware, we need to develop great software. So today, NVIDIA is proud to support all of its hardware's line with great libraries, SDKs, open source models. And what we emphasize is that the majority of tools that we develop are free and easily accessible to everyone, because our main target audience is developers, and we want them to be able to find support, to find the right tools, and do their job the best they can. At the heart of NVIDIA's acceleration is CUDA platform. CUDA is NVIDIA's programming language that you can use to program GPUs to accelerate your workflows. And it started just as a programming language for GPUs, but right now it turned into a great platform. It contains a huge number of libraries that power frameworks, that power model development and model optimization. And we're really proud of it as more people use CUDA, more tools emerge, and even more people can start using it. And as more people use it, more things are being developed. Sorry. At this slide, I want to tell you about some of the examples of where you can use it. So at the heart is, of course, hardware, our GPUs, CPUs, and DPUs. And then there are acceleration libraries. A few examples is Rapids. Rapids can accelerate your data science workflows. For example, with cuDF, you can accelerate your data frames with just replacing the import from import pandas to import cuDF. The same with CuPy. CuPy is basically GPU accelerated NumPy. And if you think that you've never wrote a line of CUDA in your life, is it really so helpful for me? Well, if you've developed any models and run them on GPUs, yes, because PyTorch is powered by CUDA libraries, and other frameworks like JAX, TensorFlow, basically everything is. And the best part is that maybe you don't even know about some libraries, but we do have some frameworks. For example, with Riva, you can generate speech and translate languages with cuOpt. You can optimize route planning. With ISAC, you can develop robotics applications. And with Modulus, you can simulate physics. Let's take a look back and see how the software has changed throughout the recent years. So we started with software 1.0, which was hand-programmed, heavily logics-based. What we write, that executes. And CPUs were perfect for that. But now we're moving towards software 2.0, AI, machine learning. It's not just the rules that we hard code, that we program. Now our software learns from the data we give to it. So the better the data, the better it learns. The more data we have, the more our models learn. So we need to keep feeding it, and we need to do it efficiently. And that is why the demands grow and demands change. Let's take a look at how the AI has changed throughout the last 13 years. So basically, everything started in 2012 with AlexNet, when at the University of Toronto, AlexNet was powered by NVIDIA's GPUs and CUDA and beat the ImageNet benchmarks. Everyone understood, yes, this is the right application. This is what can help us achieve great results way faster. Some people even say that NVIDIA's acceleration allowed them to do the work of their life and be sure that they will live until the advancements they were hoping for will happen. So the next step were GANs that powered the generation. And then there were transformers. And with transformer architecture, we now knew, okay, we can generate language and we can not just have fun with it. Actually, it has a lot of powerful applications for many areas. And we were sure that now AI does not just do what we told it to do. It does not only show us what it saw, like this is a cat or this is a dog. It can actually generate knowledge. So the next step is agentic AI, where we will have multiple agents that will be able to interact with us, interact with each other. They will be able to interact with other tools. And they will be able to do, basically to make our lives happier. I'm not sure, but happier, definitely easier. And the hope is that they will take on laborious work and tasks that we're not super thrilled about doing. But I'm actually excited about the wave of AI that will come after agentic AI, and that is physical AI. Because this is really great that now you have all of those chatbots or RAG or other models that help you generate knowledge, generate images, generate text. But imagine having a robot that can help you do actual tasks that will interact with the real world, that will interact with you in the physical world. And with that, I'm really happy to transition to NVIDIA Cosmos, a suite of NVIDIA's World Foundation models and NVIDIA World Foundation Model Development Platform. And let's start with a video that will introduce us to it, and then we will dive deeper. Okay. Oh, sorry. Thank you.
The next frontier of AI is physical AI. Model performance is directly related to data availability, but physical world data is costly to capture, curate, and label. NVIDIA Cosmos is a world foundation model development platform to advance physical AI. It includes auto-regressive world foundation models, diffusion-based world foundation models, advanced tokenizers, and an NVIDIA CUDA, an AI-accelerated data pipeline. Cosmos models ingest text, image, or video prompts and generate virtual world states as videos. Cosmos generations prioritize the unique requirements of AV and robotics use cases, like real-world environments, lighting, and object permanence. Developers use NVIDIA Omniverse to build physics-based, geospatially accurate scenarios. Then output Omniverse renders into Cosmos, which generates photoreal, physically based synthetic data. Whether diverse objects or environments, conditions like weather or time of day, or edge case scenarios. Developers use Cosmos to generate worlds for reinforcement learning AI feedback to improve policy models, or to test and validate model performance, even across multi-sensor views. Cosmos can generate tokens in real time, bringing the power of foresight and multiverse simulation to AI models, generating every possible future to help the model select the right path. Working with the world's developer ecosystem, NVIDIA is helping advance the next wave of physical AI.
Okay, great. Thank you. Hope you enjoyed it. And with that, I will transition to the 3-computer solution to build in physical AI. It will be a small introduction before diving deeper into Cosmos. So developing physical AI is actually pretty hard. Basically, we have to do what we did before and then do some extra steps. So the step 1 is having the pre-training and post-training processes, and that we can do with DGX, so like regular computer that will run our AI models and train them. Then we're talking about physical AI. It's not just enough to train some model. We actually have to test it. We have to simulate it. We have to make sure that it does what we want to do and does not harm anyone. And for that, NVIDIA has Omniverse. Omniverse is a simulating platform where we can test out everything that we have developed. And you can actually too, if you want to use it. And the last step is actually deploying our physical AI into the real world with NVIDIA Jetson and Thor. And then after we gather data from our simulations and hopefully from the real world after deployment, we can retrain it and make our models even better. But again, this is very, very costly. Data is hard to find. Data is usually messy. We have tons of videos and then we don't know how to process them. We don't know how to filter them. And we cannot waste our precious compute resources on just training our models on anything. And at the end of the day, the results are only as good as our data. So this is where NVIDIA Cosmos can be really helpful for you. Let's talk about also edge cases. I will talk about it a bit more later, but a great example where simulated data sets are actually very helpful is edge cases. So imagine a child running out on the road or something falling from the building. We need that data because the world is not perfect. Everything cannot go smoothly and as we want it, but we cannot risk children to create good data sets. We cannot risk workers dying during the constructions just to make sure in the future no one dies. I know people did that before, but we'd really like to avoid that. So with that, we're coming to the overview of NVIDIA Cosmos. It's not just models, it's a whole platform. Yes, the first part is Cosmos World Foundation models. And actually there are 3 main classes of them: Cosmos Predict, Cosmos Transfer, and Cosmos Reason. And I'll tell you now, actually they're all open sourced and available, both pre-trained models and tokenizers. And the last one, the reasons, they were open sourced just 3 days ago. So they're actually really fresh. The next step is data curation with Mimo Curator and video dataset search. As I said, we actually have a lot of data. We're just not sure how to use it optimally and how to make sure we're not wasting any resources. And that's also where tokenizers become very useful because we no longer have to feed just a huge video. We can tokenize it and it will decrease the amount of data we're feeding into our models. And then there's, of course, post-training, because those World Foundation models, they're like foundational LLMs. They know a lot about everything. But if you want them to be really good at specific tasks, you, of course, have to post-train them. Let's take a closer look. World Foundation models, there are 2 of them, Diffusion World Foundation model and Autoregressive. I will talk a bit more about them a bit later. Then we also have advanced video tokenizers, also 2 types, continuous for diffusion models and discrete for autoregressive models. Video processing and curation pipelines, we will also take a deeper look into them, how they can help you create better data sets overall, and also how you can curate your data sets for post-training. And of course, the post-training scripts, as we really want people to adapt and use what we're working on and give us feedback, the post-training scripts are open sourced. You can access them. I will give you resources at the end of the talk. And I really hope that you will take a look at them. I was supposed to mention it earlier, but the main goal for me is I really want you to walk out from this talk either with new ideas or figuring out new tools or just realizing the art of the possible. Okay, let's go into the Cosmos World Foundation models. Why are they so great? Because they were trained on huge amounts of data, more than 20 million hours of videos, more than 9,000 trillion input tokens, 2,000 plus hours of training. And also they're foundational models because they know a lot of data. Data is incredibly diverse, whether it's data can be used for humanoids or autonomous vehicles or just general knowledge about the world. All of it was used and just for better. There are 3 classes of world foundation models that we develop. First one is Cosmos Predict. It generates future world states based on either text or videos that you feed into it. For example, you feed into it a video of a car driving on the road, and it will generate a few next frames. Or if we're talking about robot on some factory, you describe the setup, you describe the robot. You don't even need a video or image, and it generates a robot based on its understanding and your prompt. The next one is Cosmos Transfer. Honestly, my favorite. This is where you combine NVIDIA Omniverse and NVIDIA Cosmos. You can create 3D scenes in Omniverse and then use Cosmos transfer models to make them look realistic. Again, the example was the car. You can create a 3D scene of a car driving somewhere, and then you can use Cosmos transfer to either change the weather or change from day to night. And with this, from one 3D setup, you have multiple frame data. And the last one is Cosmos Reason, the one that was released 3 days ago. It uses chain of thought reasoning for physical AI world state understanding. So you can actually ask questions about the videos you're feeding into it. And you can also ask it to make decisions for your physical AI, for your robot or for your car. Again, we will take a closer look. So this is Cosmos Predict. As I said, we're feeding it in either text or video or start and end image. And then it will generate for us a world. It's built as generalist to post-train for robotics and autonomous vehicle development. Cosmos Transfer for robotics, we take a 3D scene, we take extra data from sensors like LiDAR or 3D maps, and then with Cosmos Transfer, we create photoreal videos. This is the example of Cosmos Transfer for AV. We generated a photoreal video of car driving in the fall, and then we can turn it into winter, spring, or even night. And now onto Cosmos Reason. It's available now. And as input, it gets a video that we're going to reason about and a text prompt. Then it executes chain of thought reasoning and answers our question. For example, what are the possible actions this robot can take? For example, pick up nearest object using right arm. And we will take a look at better examples as well. For example, with autonomous vehicles, it is able to predict a next behavior of the driver in the video, and it not only gives us its decision, it's not a black box. We can trace the way it thinks. It will reason about the question, our prompt, it will reason about the video, and then it will give us its answer. And exactly the same for robots. It will take a look at the video of what's happening in it, then it will process our question, and then it will reason about it and tell us that to open flap of the brown box, we need to move the gripper upward to lift the flap further and fully open the box. Now, we have those great models. What do we do with them? We can customize them. And for that, we have 5 great tools. First one is NeMo Curator, where we can filter our data sets, make sure the data is what we need. We have video data search. It's great for finding specific videos or maybe creating smaller data sets that we're able to use later for fine-tuning for a specific use case. Cosmos Tokenizer, a NeMo framework that helps you build, customize, and deploy foundation models. Again, open sourced. And there are actually a lot of great introductory guides on how to do it. And of course, guardrails, because we want to make sure that everything we're generating and we are working on is safe and used for good. And in terms of guardrails, there are 2 of them. First one will make sure that the inputs we're fed into our model are correct, not correct, are the ones we want. And the other one will make sure that the generations, what our model generated, it also fits into our requirements. Why is that important? We all know that AI scales hugely with new demands, but if we all know about scaling during training, so now we have more data, so we have to train for longer, there are actually 3 scaling factors that we have to encounter for. First one is pre-training scaling, the data one. The other one is post-training scaling, so using RAG, using fine-tuning technologies, using distillation. And the next one is the time scaling or long thinking. And this is important for inference because if before the models were mostly demanding during the training, now with reasoning and models generating thousands of tokens during inference, we also have to care about how optimized is our inference workflow. And we really hope that all of those models that complete the World Foundation models and turn them into World Foundation model development platform will help you make sure that you are using all of the resources available to you in the best way possible. So let's take a look at the NeMo Curator, what it can help you do and how. Let's switch to this one. So we have a video. Imagine it's a long one. Not really great start for training something. We will split it into a lot of smaller videos to make sure it fits our requirements. Then we'll transcode it and we will filter it. And how we will filter it? We will make sure that there are no clips where nothing happens. So we want to make sure that those are actually videos and they're useful for our pipeline. We will filter them out based on quality and based on how well the video describes what it's supposed to. For example, if there's some text that's laid over the video, it's not really good for training. We will just dump it. Then we will annotate it for future usage, and we will generate video and text embeddings. And this will create our great training data that we can later store and reuse. And thanks to the annotations and video and text embeddings, we can later use all of this to curate our data sets either for fine-tuning, post-training, or any other needs. Let's take a look at the NVIDIA Cosmos tokenizers. They're the thing that makes training easier because we do not have to feed huge videos. We can tokenize them and decrease their latency space. They're easily used and compared to, Okay, I will talk about it a bit later. They're easy to use. They're open sourced. Again, there are 2 of them. Continuous and discrete. Continuous can be used with the diffusion models, and the discrete can be used with autoregressive models. And they are great at both encoding videos and images, and also at reconstructing them. And at this slide, we can see the comparison of Cosmos tokenizers to other open source tokenizers in terms of spatial temporal compression rate and reconstruction quality. So not only the reconstruction quality is superior, but also the rate of compression suppresses the other open source models. Not for every tokenizer, but still. And what's more important, I guess, is that the quality remains very high. So how can you fine-tune your Cosmos World Foundation models with NeMo? I will go through the slide step by step. At first, we have our video data that we're going to work with. Then is the data that we want our models to fine-tune on. Then we use our video data curation. Another important note, all of these components are extremely modular, so you do not have to use this pipeline from the very beginning to the very end. You can switch and swap any components that you like or don't like. It's just a reference workflow of how it can be done using the NVIDIA technology. After we created our data set, we're tokenizing our videos together. And then we're moving on onto continued training. Then we're evaluating our model, and now we're ready for inference deployment. And what's coming next is NVIDIA inference microservices optimized for Cosmos models deployment, as well as NVIDIA TRT LLM and Triton. There are many alternatives that you can use, but I'd recommend you test and try it out what works best for you. And now onto the Cosmos guardrails. As I said, Cosmos guardrails will make sure that your models do not go off limits, and that both data that comes into your models and the data that your models generate is the way you want it. And another thing is that it can place digital watermarks on the synthetic videos generated, because we want to be transparent and make sure that our developments do not harm anyone. And we also want to be transparent about AI-generated content all over the internet. Have you tried looking for a picture of cat on Google Images? It looks like no one knows how a real cat looks anymore, because all of them are AI-generated. And if you want to try out how NVIDIA Cosmos World Foundation models work, there are a few examples that you can do anytime from anywhere through your browser completely for free. Is on build.nvidia.com. There you can access Cosmos Predict NIMs. NIMs are NVIDIA inference microservices that are optimized for inference. So it's basically a Docker container in which you put a model, not you, NVIDIA engineers, and optimize it for inference. All you have to do is just use them, and it helps you avoid a lot of work and saves you time and money, I would say. So this is how it looks. At first, we can choose what kind of model we want to use, either text to world or image to world. In this example, we're using text to world. Then we're given our prompt of what we want to generate. Here, I guess it's a robot on some factory. We know that not always we can create the perfect prompts, so AI has automatically improved them. And unfortunately, I cannot show you here, but I bet you saw it in that video, that it's actually a video and not an image. Let's talk about use cases, about NVIDIA Cosmos and NVIDIA Omniverse and NVIDIA Cosmos Transfer Model. So we have our virtual world that consists of NVIDIA Omniverse and Cosmos Transfer Models. And by using them together, we can create our synthetic data that will replicate the real world, and not just visually, it will also make sure that physics is contained. Let's take this look. So here, we're taking the 3D scene from NVIDIA Omniverse and then applying Cosmos Transfer to it, specifying how do we want the environment to look like. And our output is a photorealistic image of a humanoid robot interacting with the world around it. The same thing can be done to the vehicles. We're creating a city scene of a car riding somewhere, and then we're applying it, and now we have a car riding in a fall. So we want our data, synthetic data, to be physically grounded. Because if we want to reason about the real physical world, we want our data to represent it. So we cannot have a robot walking and then turning into a different robot, or the objects that the robot interacts with suddenly disappear. And this is why the combination of Omniverse and Cosmos is so powerful. And you can not just use the 3D layouts, you can use text, you can use data from LiDAR, you can use 3D maps, all of it to make sure you have the best quality data. This is the example of how you can generate diverse real-world data. And I want to show you a video of some examples of how Cosmos Transfer Model was applied to create great real-world data. And I think I will need some help with that. Thank you. Thank you. Okay, now let's talk about blueprints powered by Cosmos. Blueprints are NVIDIA's reference architectures. NVIDIA does not build solutions. We build building blocks, but this is our way of saying, if we were to build it, this is how we would do it. And the first one is Isaac GR00T for synthetic manipulation motion generation. Basically, it tells for itself. Isaac GR00T is a set of tools for developing robotics. And here we can see how with Cosmos and Omniverse, we can develop multiple scenarios to later use those videos to train our robot manipulators. And the next one is NVIDIA Omniverse blueprint for AV simulation. Here you can see the building blocks for simulating AV. And so, yep, and it uses Cosmos transfer model to create post-processed videos, the Omniverse to generate it. Okay. Where to begin if you want to use it, if you want to develop it, if you want to either use the models or fine-tune them, or curate your data sets, or just learn more about World Foundation models. The first place to go is build.nvidia.com. There you can find NIMs and also blueprints, and not just Cosmos related. There are a lot of NIMs for large language models like Llama, DeepSeek, I guess. It has a lot of things you can explore, and again, it's free, it's easy to use. You can access it basically from anywhere, and if you're interested, it shows you next steps on how to use it for your productions. Then, if we're talking about the Cosmos World Foundation development platform, Cosmos models, Cosmos tokenizers, are available on Hugging Face and GitHub. And if you are wondering where to start with, and you're not sure, you're not very fluent with developing models or fine-tuning them, there are a lot of introductory resources and guides on how to do it. You just have to Google NVIDIA Cosmos VFMs, and it will lead you to NVIDIA's website, where all of these resources are linked, and you're really welcome to use them. And also, we have a few starter kits for synthetic data generation and for post-training Cosmos VFMs. So you can get access inference script, workflow guide, post-training scripts, the documentation, of course, and also if you're interested in some tools that are not yet openly available, you can inquire about their early access. And I suspect the majority of you are developers. So if you want to make your developing journey a bit easier, you're welcome to join the NVIDIA Developer Program. It will guide you to open resources, to materials, to libraries, to SDKs, to other open models that you're, of course, welcome to use and share your experience, and also to the developer forums. Thank you so much. Thank you. And if you have any questions, you are, of course, welcome to ask them. I'm just not sure about the procedure. Okay. Okay, great. Have a great day. Oh. Oh, I'm sorry, I didn't see it. Okay, good. Then I'm waiting.
Am I audible? Can you hear me?
Yes, sorry.
As far as I could, first of all, nice talk. Thank you so much for delivering this. I wanted to ask, is NVIDIA, I see that it's all about physical world. As of now, I could see robot arms and mostly, for driving use cases. I'm just wondering if NVIDIA is also looking into video understanding in general. Are this working on, can I have the reasoning of, let's say, in a video, a person is doing an activity. Let's say a person is running or doing some physical activity. do the current models also support the predicting the next actions of what the person could do, or just wanted to understand what's happening and at NVIDIA this time?
So these particular models, their goal is to accelerate the development of physical AI with a focus on robotics and autonomous vehicles. So you can definitely try, since the data they were trained on is really diverse. Maybe something good will happen, but it's not what they were trained for.
Okay, I see. Okay, thank you.
You're welcome.
Just a quick question. Does NVIDIA have foundation models for medical imaging? As far as I see from the presentation, the images are so-called natural images or like natural videos.
Honestly, I do not work with them. That is why I am not aware of it. But I'm not saying NVIDIA does not have them. My best guess would be to go to the NVIDIA's website and explore, because if we are working on it, it's definitely linked there.
Oh, thank you.
Okay, any other questions? Okay, I see.
Yeah, I've got a history of asking stupid questions to smart people, so if you don't mind. So the industry I work in is oil and gas, but I have a background in physics at the U of A. So when you were talking about physics-informed simulations, and I was starting to see that scaled up, my immediate thought was, how do we take not just the video interpolation and industrial application within warehouses, but what about digital twinning? Like we have large continental scale systems that have real-time feedback loops, and sometimes we want to optimize that. Or planetary simulations with plasmas, that kind of thing. So just kind of curious, the physics simulator that you have in Cosmos and DB, how generalizable are they? Are they based on CFDs, physics simulators, or how are they trained? How widely applicable are they too?
Okay, so as I said, they're mostly at this point developed for robotics, humanoids, and some like arm manipulators and robots that may be used in warehouses, and also autonomous vehicles. A lot of work is being continued. In terms of physical simulators, well, Omniverse is used. If you are asking for specific applications for oil and gas,
pipeline optimization, that kind of thing.
Well, there are a lot of other tools that may partially use some work from Cosmos World Foundation models. Like, for example, if you're talking about smart factories, we have Metropolis. This is a framework that helps build them. We also have something called virtual factory integration. It's not tied to Cosmos World Foundation models, but it might solve the problems that you, like, not the problems, might be a good solution for your use cases.
Okay, thank you.
You're welcome.
Hello, thank you very much for the very good presentation. So from exploring the website and many of the videos I've seen, it seems most of the videos generated are very short, like 5 seconds, 10 seconds. Was it trained that way?
So there are two kinds of models, diffusion models and autoregressive models. The difference is that diffusion models, they generate better quality videos, but they can only generate pretty short ones. It's longer than 5 seconds, but not too long at this point. But with autoregressive models, the way they work, they take either text or image or video as an input and then generate the next frames. So you can just keep feeding the model frames previously generated by it, and this way you will be able to create longer videos.
Oh, like a loop.
Yes.
Okay, also you mentioned fine-tuning the model.
Yeah.
Like how many hours of video would you recommend to fine-tune such a model?
I think it depends on the use case, and you'd have to inquire.
Especially if it's like longer videos that I have.
Yeah.
Right?
I don't know.
Okay, thank you very much. I'll look through the resources.
Okay, great. Okay, if there are no questions left, thank you so much. You're a great audience, and I was very happy to be here. Thank you.